You're listening to the Effective Statistician podcast, the weekly podcast with Alexander Schacht and Benjamin Pieske, designed to help you reach your potential, lead great science, and serve patients without becoming overwhelmed by work. Today, we are taking an episode from the sister podcast, The Effective Data Scientist, and put it here on the show because this episode is also really helpful for any statistician working in the healthcare industry, because interpretable output from machine learning algorithms are really important. And if you think like, well, that is something for data scientists, stay tuned. Even with a little bit more complex logistic regressions and these kind of things, these can be really helpful. So have fun listening to this episode. Given that you listen to this episode, given that you listen to this podcast, maybe you're regularly listening to it, I know that you love to invest in yourself, into becoming a more effective statistician. And now there are lots of further opportunities to upskill yourself. And all these different opportunities come with the Effective Statistician Academy. We have outstanding course creators there that work together with me to create really good training for you. So check out the Effective Statistician Academy, look into the show notes, or just check out theeffectivestatistician.com/academy. As this episode goes live, the PSI conference is just around the corner. If you can't attend, well, then at least make sure you block the time for next year. It's an outstanding conference. It's probably the best conference in the stats for healthcare people that you can find. Maybe next to my conference, of course, but that's another topic. So check out PSI at PSI website, psiweb.org, to learn more about all the different things PSI does and how you can become a PSI member today. Welcome to a great discussion that we'll have today about machine learning. Hi, Paolo. How are you doing?
I'm doing very well, Alexander.
Very good. Hi, Serge. How are you doing?
I'm good. Thank you.
Very delighted to have you as a guest on the show. So maybe before we dive a little bit deeper into the technical topics, can you introduce yourself to all those who have not heard about you and your book and things like that before?
Yeah. I'm a data scientist in a large agribusiness company. What I do there a lot involves predicting plant disease and plant growth and things like that. The reason we do that is to enable the farmer to make better decisions in order to lead to more sustainable agriculture. And so in a way, it's disrupting the very essence of the way agriculture is done today, even by the company I work for. So it's like we're disrupting ourselves through these methods. Prior to working here, which is 2.5 years ago, I worked in a 3D printer manufacturer company. And what I did there was I was the first data scientist in that company. So kind of tried to lay some groundwork to what needed to be done to take it to the next level data wise. And before that, I was actually studying data science, but as getting a master's in data science. But that precludes the fact that I've been working for data for over 20 years. Difference is the roles before I officially became a data scientist were in the web space. Data was always coming in. I was always analyzing data as the webmaster for a large online poker operation. So there was a lot of data coming in and a lot of analysis. And my role there was trying to connect the dots and figure out what had to happen with the website to improve operation and reduce friction with sales and things like that. Yeah, before that, I did a lot of things in the web space, always touching on data. I also was an entrepreneur. I had a startup also involving machine learning. And yeah, it's been a long journey. All I can say.
When got you infected by the machine learning and data science bug?
Oh, it's like you think you love something and there's something in the background. Like, it's like I got involved in the internet. I thought I loved the internet. That's what I love. But the internet the reason you love the internet is because it has all this information. Once you understand this information well enough, it's no longer, it's data, right? And I didn't realize that's what brought me to the internet. That's why I was interested in it. I thought I was interested in building stuff on the internet. I thought I was interested in websites and mobile apps and all that stuff. But reality, the building part of it stopped interesting me a long time ago. What kept me going was the data. I was more interested of the data coming in than the data going out. And I got obsessed with SEO and web marketing and A/B tests for websites and all sorts of things on more that end, on the analytics end and on the actual building it. So I guess I had fallen in love with data and I didn't realize it. So it's like one of those stories. There's you think you fell in love with one girl, but there's some other one that's always there. That's the one that was for you. The girl next door, right?
You started with programming and then diving into
Yes.
data, while other people maybe start with the data and then dive into programming. But
I always connected both. That's the strangest thing. I learned how to program when I was like 8. I had barely learned how to read and write, and I was already programming. But it's not like I was programming whiz or anything. I was just doing the sort of simple thing you would do back then. Commands, and it was basic, Microsoft Basic. Think of old school, like monochrome screen, just like doing silly things like, okay.
Can completely relate to that.
Yeah. But I was always interested. Once I got involved in the programming more enough, I was interested in the data side of it because around the same time I was learning about computers. My parents were also learning about computers. I think late 80s, early 90s. And my mother is working with databases and spreadsheets. And she asked me for help with that sort of thing. And I'm like, oh, what's this? And I get interested in that stuff. So I start making databases for maybe we have only, I don't know, like 100 albums in the house, CDs and cassettes and whatnot. And I'm like, I'm going to create a database for this so people can find it. And it's a ridiculous use case because it's not like we have a huge catalog, but I'm just trying to find reasons to create databases. And as for spreadsheets, like I start to use spreadsheets for like decisions I have to make. So I'll create what classes do I want to enroll in high school next year? And so I'll rank them by things. Oh, how much do you like this professor? I add a coefficient, I multiplied. So it was second nature to me. But for me, I thought it was all about the tool and not the data. To me, it was like, okay, I'm trying to work with the tool. So it went hand in hand. But as I said, I didn't realize data was always there and data is what I loved. And programming and databases and all that stuff was just tools to get the things done that I wanted to do with data.
Awesome. So you really came from the application area. You needed to make decisions. You needed to use the models. And it's very similar for me. Yeah. Also, I studied mathematics. Yeah. When I was always coming from what was the questions that I need to solve here? Do I need to find kind of predictors for a disease or for a treatment or for an adverse event or anything like that? And then I was thinking about what is the right tool to use. Whereas I think a lot of people also think about, well, I absolutely want to use this new cool tools or methods that I just used about. So let's find a problem that kind of might fit to it.
Yeah. Yeah.
So your book is very much about interpretability.
Yeah.
Machine learning. What does that actually mean?
Okay. There's interpretability and explainability. And it's confusing to talk of both because as we're talking, there's still a debate. Not so much in industry because most people understand them to be the same thing. In the same way people understand machine learning and AI to be more or less the same thing. But people do split hairs about these definitions. I've chosen a camp, and in my camp, interpretability is the ability to interpret anything through any means, as long as there's some level of truth to it. And that includes what is called post hoc interpretability, which is like interpreting something that is a black box in nature. You just have the inputs and the outputs, and there's a level of assumptions that are made, but you're making a connection between both. That is a totally valid interpretation method for me, post hoc interpretability. On the other hand, explainability to me, and this is what the school of thought I've subscribed to, explainability try to go deeper into that, and you have to get into the guts of the machine, get under the black and understand exactly how it was made, which for black box models is pretty nearly impossible given the level of parameters going on. So it's a very difficult machinery to try to unravel.
It's a more ambitious task.
Yes. So they're precisely statisticians. It's mostly in the statisticians and some people in the ethical AI camp that have the definitions reversed. So they think, okay, explainability is what you do with black box models. Interpretability is what you can only do with white box models. Okay. And one of the reasons I don't like that is just simply semantics. I think if you were trying to go with levels of confidence between both terms to interpret something, you don't have to really understand, how it's made, whereas explainability you do. Explainability is like to explain something, you really have to understand everything. That's my take on that. It's just a word, and that's the way I relate it. One has far more gravitas than another.
You mentioned black and white box.
Yeah.
These are other interesting terms. Are all black box models not explainable and all white box models are explainable? So it's the same?
No, I think there's a lot of gray area there. I think people talk of white box models, they're classes of models. And if you have a linear regression model with, 100 features, I got to tell you, that's not explainable. There's no way. And by the same token, if you have a decision tree, which in theory is fully explainable, and it has 10 levels to it, you can't explain that. There's no way you can. To me, to be able to explain a machine has to be like the sort of thing that at a glance, like on a very, you can explain it, you can understand. It's like you can save the entire model in your head and you know exactly how it works. And if not, it doesn't make sense. If you have to really look at all the interactions between all the different things and figure out how it all maps out, you can't explain it, I think, honestly. So that's my take on white box models. I don't think you can say for sure that all classes of certain kind of models are fully explainable. And then as for black box models, on the other hand, I think they have a bad rap. I think there's a lot of cases in which you can look under the hood. You can take a convolutional neural network and get a pretty good idea of what's happening in every layer, in every node. You can do that. Of course, it has to remain once it's, same thing I said about white box model. Once you're like dealing with 10 layers upon layers, like a very deep neural network, you can no longer do that, I think, and truly say, oh, I understand it. I understand what everything's going on, because it just becomes too complex.
I was quite intrigued by another definition, which is glass box model, and I never knew about it.
Yeah.
Please explain a little bit.
That's a term. I don't know if it's trademarked by IBM or is it Microsoft? I think it's Microsoft. Yeah, I don't know if it's trademarked by them, but they created what is called EBM, explainable boosting machines. And they operate on something called GAMS, which is generalized additive models. And the way GAMs work, they just simply keep every feature separable because it's fully additive. And that property is a very desirable property because one of the things that makes machine learning models so difficult to understand is how entangled every feature becomes with each other. It's what is typically called in statistics multicollinearity and interaction effects and all that. It just becomes too messy. And so if you have a GAM of any form, it's highly interpretable no matter how many features it has. Of course, I wouldn't say necessarily, of course, if you have 100 features, it becomes less. But by the fact that you can separate every feature and measure their impact, that becomes very desirable. Going back to the term glass box it sits in the middle between white box and black box because of the fact that it can achieve performance very near or like black box models can have. Because people keep using black box models, quote unquote, because for two reasons. One, because there's no other way to do what they want to do with a white box model. And that's the case for convolutional neural networks. You would never do like an image classifier in a linear model or decision tree or anything like that. Or because you want to achieve a predictive performance that you couldn't possibly achieve with a white box. Of course, there's people that make that a rule and say, okay, I'm always going to go with a neural network because it's going to achieve or XGBoost or something. And that's not always the case either. So I have to state that, but it's not like black box always rule in that sense. But in cases when they tend to rule, people ought to learn about glass box models. So there's more and more research being done in that field, including by Wells Fargo. And they have some amazing models that came out. And the interesting thing about glass box is that more often than not, it has that GAM component. So it's either a GAM component or a rule-based component, which is very interesting that you would take those two different properties and make them into models.
Very good. Now, I have a follow-up question on the interpretability. You speak in your book about model agnostic methods for interpreting models. What is that?
Model agnostic methods. Okay, you got model specific methods, and the model specific methods rely like on the intrinsic properties of a model. So intrinsic properties of a model are like getting into the guts of the machine and figure out what kind of crazy math is going on inside that turns what's coming in into what's coming out. And things of that nature are like for a linear model, that would be the intercept and the coefficient. For a decision tree, that would be the splits and all the way that's structured, all the different nodes, and so on. There's so many different ways to define the coefficients. For a neural network, for instance, that would be the bias and the coefficient, right? Those are the intrinsic properties. So any model agnostic method will leverage those intrinsic properties. Model specific methods.
Yeah.
Model agnostic methods, it's either doesn't have, let's pretend there's no access to the model, to those intrinsic properties, or it has access and just chooses to ignore it. But the model agnostic methods only need the input and the output. Sometimes not even the output, but mostly the input.
So it could be if you think about a classification problem, it could be all different models that lead to this kind of classification. Could be regression models, could be other models, all kind of different things you could do. And these model agnostic methods for interpretability would always work.
Yeah, it doesn't matter because they treat the model as a function. So to them, the model is like any function. So a lot of people don't think, like one of the oldest model agnostic methods is sensitivity analysis. It's been well known for decades now.
You change your input, which kind of output?
Yeah.
Change the model, right?
Yeah. So a lot of them work like that. So the idea is you give it they work best when you give them an idea of what kind of inputs the model expects. So you at least have to tell them how many features, but usually they expect like a sample or something. So you tell them, this is more or less the distribution of the data that goes in, and they permute that. Or you give them one example and they permute it. And by permuting it, it's like adding noise to it. So they add noise to it to figure out exactly how much is impacted on the way up. And that's how most of them work, but not all of them. Some of them have variations on that theme, or they do something else. Some of them are not entirely model agnostic. They're aided a little bit by the intrinsic parameters, whether it's the structure of the model and so on. One of those libraries is called SHAP, and there's so many variations on the same thing. They're just leveraging like a permutation method, and sometimes, depending on the model, can be guided by the intrinsic parameters.
Nice, because in general, you may think that when you deal with problems and you need machine learning techniques, many people think that you lose the interpretability.
Yeah.
While reading your book, it seems that in many cases, it's possible to interpret your model. There are, of course, exceptions, but in many cases, it's possible to deal with machine learning techniques and having the interpretability. And there's a moment when you read this kind of discovery.
Yep.
Yeah.
When I first, even if you do very simple, let's say you do a cluster analysis, yeah, and you want to understand, okay, with my current data set, looks like there are 4 clusters. I take maybe just the females or just the males. Is it still 4 clusters? Or if I take just the older, just the younger, is it still 4 clusters? You get a sense for that.
Yeah. There's so much you can do. One of the things that I find beautiful about interpreting models is the fact that you can go deeper. A lot of people think, okay, I'm just going to run feature importance and that's it. And so I'm going to rank my features by how much they impact out. And that's really a shame. That's like probably the first thing you do, but you probably want to also take it down a notch into the clusters, as you say, and see different segments and say, okay, these are the most important features for everybody, but what are they for the males versus what are they for the females? What are they for people that make income over this versus, and then you start to see other patterns emerge. And so it's going down to that level and see if there's disparity that might figure out something about fairness, if there are problems with fairness, if there's inconsistencies that might lead to, you think, maybe this model it won't generalize well. Maybe it's not very robust, or maybe it won't do well under these circumstances. In the book, I have an example with traffic, and I say, okay, if it's a holiday, all bets are off. You should probably not use this model. It's a holiday. So there's a lot of cases, and you should know these things about the model. You shouldn't go out to your clients or if you work in the company dealing with these models, to your stakeholders within the company and tell them, oh, use this model, and don't tell them much more. You should put like caveats, like asterisks, and say, oh, under these circumstances, maybe not. Be careful with this. It's not only for ethical reasons. It's just good business practice, I believe.
Completely agree. The typical kind of question for that in my Master Institute was always, what happens at the margins? So if you go to the extremes, what happens there? When will it break down? And so understanding these kind of things is really important. As you talked about ranking, what are the most important features? I've seen so many reports where people say age is a predictor and gender is a predictor and whatsoever. And you're left with, in which direction actually? Men's worse off or females worse off? And it's not included there. It's just a variable. Yeah. And then, of course, that leaves you, it's important, but in which direction?
Yeah. No, definitely. I think that's why digging deeper beyond the general ranking, there's feature summary visualizations like partial dependence plots or SHAP zone dependence plot, or you can also use a nail plot. It's even better. And then you start to see these patterns. It's not just a question of this feature is important, but how? Is it like say, for instance, income. Does it have a monotonic relationship with outcome? Or like, I also have this example I present at conferences about the scholarship prediction problem. So you want to see who's worthy of a scholarship, and you have grades, the grades of the students, and you would think that the grades, high grades, correlate with getting a scholarship or not. So you want to see that in the data. And if you don't, you want to ask why.
Yeah.
And maybe you even want to make sure that this monotonic relationship is withheld in the model. Because even if you have not a lot of people with very low scores or exceeding like high scores, you want to maintain that relationship no matter what the model gets. Because like outliers will happen in production once your model's out there, and you want these relationships to continue regardless of what it gets.
Yeah. So that's built-in interpretability.
Yeah, that's
So
the flip side. Yeah.
You're giving constraints to your model in order to interpretable, right?
Yeah. Yeah. There's you can do that. You can add constraints to the model to make it more interpretable or make it more fair. There are a lot of people, when it comes to fairness, they look at just the outcome, but there's also, that's a kind of fairness, looking at the outcome. But you can also, there's like rules that people associate with fairness that have nothing to do with the outcome, that have more to do, okay, this is the way it's built because that's what's fair. It's fair that the people with a higher grade are more deserving of the scholarship, regardless of what the data says, because maybe the data is sparse, or maybe it's noisy, or maybe there was some other historical reason for it to be skewed in one way or another and biased. There's many reasons to do that, but I advocate like looking into that, figure out what things are monotonic or linear or have some kind of pattern in the data, and the model can find, and we can improve, we can enforce, we can strengthen. I call that putting guardrails.
Yep. Yeah. I love that you mentioned data visualization. That's also my kind of go-to area when I want to understand what's going on here. When I want to see patterns, when I even want to understand directions, how big impact certain variables have, or whether interactions and whether there's inconsistencies and all these kind of different things. You mentioned a couple of different plots for that. Is there some kind of library or example list, or is it all described in your book and so let's buy the book?
Yeah, there's a lot of libraries, more and more all the time. Right now, I'm writing the second edition, and there's just so much I have to update. More libraries out there, very good libraries. Ones that I don't even want to mention necessarily in the book because they haven't, even though they're good, I don't know if they'll stay on, because that's something that happens in this ever-evolving field. People have come to the expectations that the libraries they like, and whether in Python or are there, and people are well known, but they start from somewhere. Someone writes a library, and if it takes off, it starts getting a lot of stars on GitHub and downloads and pip and so on. But sometimes you find and especially in the space of XAI, you find a ton of libraries that are awesome, but for some reason, they're not well maintained. So 2 or 3 years of nobody touching them. And it's sad, really, but I can't, as much as I like those libraries, I can't feature them in the book because I don't know if they'll work a year or two from now.
That's a problem. The open source, which is great because you have a lot of resources, but these resources need to be maintained. And okay, there is a community, but it's really an demanding task. So it's really difficult to. And I know that right now we have some kind of movement like the Tinyverse, for example, in ARM, in order to work always with the basics instead of using the most recent libraries and trying to develop using the basic stuff of the language. I mean, in order to keep the product sustainable in the long run, because otherwise you're not going to find the same library 2 years working in your package or production environment.
Yeah, that's why I took on some of those things myself. If you notice in the book, I wrote a library for it. At first, it started just simply for loading the data sets that I wanted for it. And then I started adding like all kinds of functions that did things that I do all the time. But I didn't want to have to copy and paste it in the book and have people like deal with all this additional code, because they really do simple things for visualization sake. Like, for instance, one that I do all the time is you have a confusion matrix. And people, something they don't realize is confusion matrix, it's just like another visualization. It's a starting point. Like you typically only see it in terms of, oh, this is the entire performance of the model. But you can break it down and compare confusion matrix between one group against another and see how the false positive rate or the true positive rate differentiate and things like that. So I started to make simple visualizations like that and put them in a function, because no other library that I knew of would do that. I would have to do that manually. I didn't want to make it complicated for the readers. So I threw that in there. And there's a lot of visualizations I did that because it's so important. I think people relate to visualization to statistics, to just looking at the data. And they don't realize that you can do the very same visualizations to the model's outcome and tie things together. And then compare them and see, okay, what the data has, this is the relationship seen in the data, the pattern seen in the data. And this is what the model captured from that.
Yep.
And ideally, you can have the same visual, and it's more or less the same. Of course, it's not going to be exact, but you want to make sure that there's alignment there.
It's one of the simple things. Yeah. If you start with a linear regression, you probably want to have a scatter plot where kind of the line goes through.
Yeah.
Just to see what happens. Yeah.
Yeah, exactly.
And of course, the more complex it gets, you still want to see predicted and actual values somehow, somewhere. And yeah, you can do that on all kind of different levels of aggregation. But it's always some kind of form of data visualization.
Yeah.
Awesome. Very good. Paulo, do you have any final questions for our great guest today?
I am wondering what's coming next for the field. So what's coming for machine learning and interpretability? What are the big ideas, the future trends we're expecting? I don't know, maybe we're expecting to have no code or auto ML in the field. I don't know.
I think you came up with a very valid point there. I explain in my final chapter, I think a lot of things will happen in interpretability. We'll be coming up with better methods, but there has to be a cross-pollination between academia and industry as far as what methods work, how do they work. There's some that are very good, but they're impractical because they're very slow. There's a lot of things that need to coalesce in that sense. And there's also a lot of very valid hypotheses that haven't been tested at a grander scale, that kind of are born out of academia and never reach wider audience in industry. Things like counterfactual analysis, causal models, and so on. I think there's a lot of things that can be done with those methods. And then once you connect them with other things that are intrinsic within certain industries, like you might want to use semantic segmentation, where you take images and you break them up into parts that mean something to the model and build some kind of causal structure that explains it. You can do a lot of stuff like that. And there's people looking into that research. I think in a few years, there'll be whole families of new methods to use in the field. But I think the thing that will accelerate everything in terms of interpretability into a wider audience is going to be, as you said, no code and low code. And the reason I think that kind of goes back to what I said of starting in web development. I think the phase I associate machine learning and AI right now is, to me, it's one I relate to the growing pains we had in the late 90s, where websites were horrible, they were unreliable, there were all these browser wars going on, there was still very poor standardization going on. And I think a lot of those things something will come out. There's going to be standards that emerge for saving models, for saving model metadata, which I believe is really important for interpretability, and which will come with things like provenance, for enforcing new standards, I think are pretty common sense. When should a model expire? I believe models should always expire. Or what constitutes a high level of confidence for a model? All models, I believe, should come with uncertainty estimates. And I think, and one of the reasons I favor classification models is because I can always establish a threshold, and I can say, if you're 50.5%, it's 50.5% probable that this is the class, might as well not give this prediction out to a person. So I favor the idea of abstention, abstaining to make a prediction. Models should be able to do that. It's not the model's job. I think it's like an API of some sort that lays on top of it. But a lot of the structures that will become the future of AI haven't been built yet or are in the process of being built. I could name you like half a dozen of projects that are currently doing no-code AI solutions that include interpretability within it. And I think that's very promising because I see that's the future of this field. I actually am bothered by the idea that that's why I connected back to the 90s. So ad hoc, so like artisanal. Everybody's making like their own models, like with the code and copying, pasting things from God knows where. And so there's not really a good foundation to moving forward. And I think frameworks are emerging and people are using them more and more. People are using fast API and all that. But what bothers me about these frameworks, whether they're AutoML or anything, is that they still lack the very important component, which is interpreting. And I think for better or worse, that is the case right now. But in the future, there'll be like once machine learning engineers and data scientists are not coding and cleaning data and doing all that all day, their hands will be free to actually interpret the models. I think businesses will start to realize the value that can be untapped by interpretation outweighs by far the expense of having someone do that. And it's right now, all that expense is very much on the data end, and that's where it should be, because I think data-centric AI is definitely important. It's important to have clean data, to have reliable data, to look into the data. That's always going to be important. But interpretation on the modeling side is not something that's done. And the reason is there's so much spent on getting everything through the pipeline to the end that nobody will have time for interpretation once that's done. It's too much work.
I'm a strong believer that it doesn't matter really so much how you work, how much work you put in. What really matters is how much value you generate for your stakeholders. And I think interpretability and stuff like this, visualizing what happens when and where are the boundaries, that's where a lot of value is generated. And I see that again and again, that people stop when the job is really half done. Communicating things like that, making sure that everybody understands everything is part of the job and not just get the model to converge.
Yeah.
Thanks so much, Serge. We had an awesome time talking about interpretability, explainability, glass, white, black box things, what we can do and all these kind of different things, what are model agnostic tools we can use to interpret our data and things like that. If you haven't read the book, we'll link to that in the show notes. Thanks so much for being in the show and looking forward for the second edition of your book. Can't wait to see that promoted.
Yeah, coming out in November.
Thanks so much. This show was created in association with PSI. Thanks to Rain and her team at VVS who helped with the show in the background. And thank you for listening. Reach your potential, lead great science, and serve patients. Just be an effective statistician.